Hello friends, welcome to your channel Ulhaskumar Gokhale for learning. Today we are going to discuss the topic Uninformed Search in Artificial Intelligence Part 2. So today we'll discuss the depth first search. Let us start with the agenda. First we'll discuss search graph versus search tree. Now this is required here for this particular algorithm because there will be difference in the properties of search graph and search tree. Then next we are going to discuss the search tree terminology and search tree process. So again, this will be the review of whatever we have covered in the previous video. Then we'll come to the depth first search and then the depth first search algorithm, and then we'll illustrate the DFS with an example. Then we'll study the properties of the DFS, and lastly we'll study the advantages and disadvantages. So let us start with the first topic, that is the search graph versus search tree. Now here, as you can see, figure 1, it shows a state space graph. So the graph starts with A, and here the arcs, they are bidirectional. So A has an arc to B and C. Similarly, B has arc to E and D. Then in the second diagram, we are showing the search tree for the state space graph. So how we get this? So we start with the root node. Here in this case, A is the root node, and then we go ahead with the two nodes B and C. Then B has further connection to D and E. So here we'll show the connection to D and E. Then on this side, again we go for C. It has connection to D and G. So C will have connection to D and G. So in this way we can obtain the search tree. If you are thinking what is search tree, it is a data structure containing the root node from where the search starts. So here A is the root node from where the search will start, and then every node may have 0 or more children. So in this case, A has two children, B and C, and C has two children, D and G. Whereas here G, E, they have no children. So we call them as with 0 children. Similarly, H has no children. All others, they are having 2 children. So in this way, the node may have 0, 2 or more children. And then if X is a child of node Y, then Y is said to be the parent of X. So in this case, say E is the child of B. So B is called as the parent of E. So this is how the search tree will be obtained from the search graph. Now here G is the goal node. So we have, our aim will be to find the path from A to G. Let us see how the algorithm works. Then we have the search tree terminology. The first is the root node. It is nothing but the node from which the search starts. So here in this case it will be A. Then leaf node. Leaf nodes is a node in the search tree having no children. So for this example, G, E and H, these are the 3 nodes which are not having any children. So they are the leaf nodes. Then ancestors and descendants. So X is an ancestor of Y, is either X is Y's parent or X is ancestor of parent of Y. So that is the case. And if X is an ancestor of Y, then Y is said to be a descendant of X. So this terminology will be useful when to understand the algorithm in a better way. Then branching factor. Now the maximum number of children of a non-leaf node in the search tree is branching factor. Now in our example, the branching factor is 2. Then last term is the path. A path is the search tree, is a complete path if it begins with the start node and ends with the goal node. So that we call it as the complete path. So that will be our aim, to find the complete path. Otherwise, it is a partial path. Then let us go to the search tree process. So the search starts with the root node. That is what we have discussed. Then algorithm picks a node from open for expanding and generates all the children of the node. So we'll have something called as the open or frontier, or it is also called as the fringe. So the node will be taken from the frontier or fringe for expanding, and it will generate all the children of the node. Then expanding of a node from open results in a closed node. That means once we open the node and find the children or generate the children, then it will be going for the as a closed node. So some search algorithm will keep the track of closed nodes in data structure called as the closed. Then search tree may have infinite because of loops even if the state space is small. So this is a typical case when the search tree will become infinite. Then a solution to the search problem is a sequence of operators that is associated with the path from start node to the goal. So whatever sequence of operators, so that will be the solution. And the cost of solution is the sum of the arcs cost on the solution path. So whatever path we are having and the cost of each arc, that will be sum, and we get the cost of the solution. The search problem will return a solution, a path to a goal node. That is what will be the general process. Then let us go to the particular topic, depth first search. So depth first search always expands the deepest node in the current frontier of the search tree. That's why it is called as the depth first search. Then depth first search algorithm puts newly generated nodes in the front of the open or fringe. So they are put in the front. That's why it will always say result in expanding the deepest node first. Then the nodes in open follow a last in first out or LIFO order. That means they are implemented using the stack data structure. So the structure for the fringe, it will be the stack. So it will follow the last in first out order. Then let us go to the DFS algorithm. So as you can see here, we have the fringe. So this will contain the initial state, and then we have the loop. So if fringe is empty, it will return failure, and if not, then node, that is we are loading the node for expansion from the fringe. So if node is goal, then return the path from initial state to the node, so that the algorithm will terminate if it is a goal node. Else it will generate all successors of the node and merge the newly generated nodes into the fringe, and here add generated nodes to the front of the fringe. So here this is the place, means it will, the nodes are added to the front of the fringe. In case of breadth first, it was at the back of the fringe. So here nodes are added at the front of the fringe, and then we end the loop. So in this way the DFS algorithm will operate. Then let us go to the next, that is the example. Now here we'll consider the search space as shown in figure, and we'll show how the depth first search works on this graph. So in step 1, we will have only the root node in the fringe. So you can see here fringe will contain A. So A is shown active here. The next step, now A is expanded and it has the children B and C. So they are put in the fringe, and A is removed from the fringe. So fringe will contain only B and C. Then next we expand node B. So it has two children D and E. So they are put in the fringe at the front. You can see here C is present already here, but D and E, they are put in the front. So now in this case, if you look at the figure, so this D and E, they are the deepest nodes. So they will be expanded first, and C will not be expanded before this. So in the next step, you can see, so D is expanded and it has the children C and F, and so D is removed from the fringe. So the fringe will have C, F, then E and C, because here C and F, they are pushed in the front of the fringe. Then next we now expand C. Now C has only child G, that is put into the fringe. So other nodes will be F, E and C. F, E, so they will be as it. Then the last step, so here G is expanded and it is found to be the goal node. So the solution path will be A, B, D, C, G. So this will be returned and the algorithm will terminate. So the fringe will have the node G, F, E and C. These only nodes will be present in the fringe. So in this way, the algorithm will work. Then let us see some of the properties of the DFS algorithm. First is time complexity. So here we have to understand that the properties of the depth first search depend strongly on whether the graph search or it is a tree search. So if you are using the graph search version, then it will have different properties. So the time complexity of the depth first graph search is bounded by size of the state space, whereas depth first tree search may generate all of the, say, OBM nodes, B raised to M nodes in the search tree, where M is the maximum depth of the any node. So this can be much greater than the size of the state space, and M itself can be much larger than the D, that is the depth of the shallowest solution, and infinite if the tree is unbounded. If the tree is unbounded, this value will be infinite. Then the next property is the space complexity. For graph search, there is no advantage, but the depth first tree search needs to store only a single path from root to leaf node, along with the remaining unexpanded sibling nodes for each node on the path. So that is what we have seen in the example. So once a node has been expanded, it can be removed from memory as soon as all its descendants or childs are been fully explored. So the memory requirement in this case will be less. So for a state space with branching factor B and maximum depth M, so depth first search requires only OBM node. So that is what is the advantage of the DFS. Then another property is completeness and optimality. So we'll just go through this. The graph search version, which avoids repeated states and redundant paths, is complete in a finite state space because it will eventually expand every node. So the graph search version, if you are considering graph search, then it is a, say, shows the completeness, whereas the tree version is not complete. So because sometimes it will lead to infinite space and the search will not be complete, will not get the goal node. Then DFS search algorithm is non-optimal. So optimality, it is non-optimal because it may generate a large number of steps or high cost to reach the goal node. As you have seen in the example, the path for solution in the DFS search algorithm is longer than the path given by the breadth first search algorithm. So that is again another disadvantage. So let us go to the last part, that is the advantages and disadvantages. So DFS requires very less memory as it only needs to store a stack of the nodes on the path from root node to the current node. So that is the main advantage of the DFS algorithm. And it takes less time to reach the goal node than BFS algorithm if we traverse in the right path. If the path contains the goal node, then it will take less time. Otherwise, it may take more. And the next is disadvantage. So there is a possibility that many states keep reoccurring and there is no guarantee of finding the solution. So if there are number of loops, in that case, there is no guarantee that finding the solution in case of search tree. And then DFS algorithm goes for a deep down searching, and sometimes it may go to the infinite loop. So this is the main disadvantage of DFS algorithm. So with this, we come to the end of this video. If you have any questions, you can contact me on Facebook, Twitter, Gmail, or Instagram. Then if you like the video, press the like button, share with your friends, and subscribe to our channel Ulhaskumar Gokhale. And don't forget to press the bell icon so that you get notifications for future videos on this subject, artificial intelligence. And thanks for watching. Have a nice day.